Hey guys, and welcome back to another stream. Alright, I am pretty sure I'm live now. Okay, let me just see, confirm it, and then I think we should start programming. Alright, just a second. I'll just do this thing that I used to do the previous time I streamed. Just check if alright. Okay, I don't think I've received a mail. Usually do. Alright, there we go. Perfect. I do have the mail. Okay, so I'm pretty sure I'm live right now. But I just want to check if the connection and the audio is good. So, I can then get started on the code. I don't know why it's taking so long to load. Just a second, I'm gonna have to. So in this stream, I'll just briefly tell you what we are gonna do. Is we're gonna look at backpropagation and optimization, so gradient descent. I'll just briefly tell you what we are gonna Alright, do. Perfect. Everything is working. Look at backpropagation. So yeah, that's what we're gonna try to do in this stream. So basically, we are going to differentiate all of the functions that we have over here. So the ReLU function, the sigmoid function, and the categorical cross entropy loss function, and yeah, and apart from that, we are gonna go ahead and actually code out the backward pass in this case over here. So this will be cool. Let's just get started with this. So the first thing that we need to differentiate is, let's just differentiate the sigmoid function first, since I do think that it's a little easy to do. So what I'm gonna do right now is I'm gonna try to make it so that I can actually record my iPad screen and I can actually show you the process of differentiating this function, and so you can get a better idea of how I basically approach problems like this. I mean, what else I can say? Because that's really what I think you need to know how to do. But the cool thing is, I actually don't need to do it for these ones, just the ReLU and the sigmoid function, because I actually went ahead and differentiated them off camera, mainly because of the fact that I just could not concern myself with actually doing this entire thing again. Uh, Basically, as you can see, I've gone ahead and differentiated these two functions. It's very simple, as you can see. For the ReLU function in the last stream, I hinted that you need to use or you need to differentiate it twice because it is a discontinuous function. So what we do is we simply differentiate this term, and then we stitch it together. So we get that for every x that is lesser than 0, we need to get 0, and for greater than 0, we just say 1. For sigmoid, I just used the quotient rule of differentiation to land upon this, which is our derivative. I know a lot of people like to convert this in terms of the sigmoid activation function, and that is a good practice, but I'm not gonna do that. So now that we know what the derivatives are, we can actually go ahead and start implementing them. So I'm gonna implement DReLU. Now I actually saw this on like a Kaggle article once, and the best way to write DReLU is just do this. This works. And this is exactly all I did for DReLU. I don't exactly know why this exact statement works, but it does work. So I just always use this. So for the D sigmoid, we just need x. And now we can just go ahead and implement the equation that we have over here, which is e to the negative x and then that entire thing. So we can just do a simple return np dot exp negative x divided by np dot power 1 plus np dot exp negative x, and we have to square it, so square, and I'm guessing I need to do this. So I'm pretty sure that is actually no, that is not correct. I will need to do this over here. Yep, there we go. So that is the derivative of the sigmoid activation function. Now the categorical cross entropy function is also very simple to differentiate. It is very simple. And let me show you what that derivative is. I worked it out, and I'm just gonna take a photo. I have actually written it on my whiteboard that is right in front of my screen right now. And I'm just gonna use that photo from my iPad, and I'm gonna show you the derivative. So there we go. Perfect. So as you can see, this is like my whiteboard. It's actually glass, but yeah. Alright, so as you can see, we have our loss function over here, which is our categorical cross entropy loss function. And it's this specific equation which we looked at in the previous video. So in this case, you have to differentiate with respect to p, which is your probabilities. And in this case, since the loss function is a function of ti and pi, when we actually differentiate this function, we actually need to find out the partial derivative of the function. So we have this del operator instead of the d operator over here. I'm sorry, d notation. I don't know what else to call it. So we use del L by del Pi, and so Ti is being multiplied, and since Ti is not Pi, it is treated as a constant, and therefore Ti just remains as your constant multiple, and then we just have to differentiate the log of Pi, and since we know that the derivative of the log of x is 1 over x, this thing comes off to Ti over Pi, and then this entire thing also remains the same. Now technically this negative sign is for the entire log thing, for the it's over here, but since the negative sign doesn't change even if you differentiate for the log, it still remains in the numerator, and so nothing changes in that way. The cool thing is the negative, we don't have to do anything too crazy in that way. And so therefore the derivative of the loss function, the categorical cross entropy loss function, is just this. So it's a pretty easy thing to differentiate, as we can see. But what I actually noticed was that I wrote the categorical cross entropy loss function, but what I didn't write was the actual one hot encoding function. So currently, if you will look at it, the truth labels have to be one hot encoded when you are comparing it with the predictions. Meaning, the actual label, for example, we have a 0 through 10. So the truth label matrix will be a matrix of size 10. I'm sorry for that. And it will contain elements. And the element, let's say the first element is the correct answer, then that element will be 1, while all the other elements will be 0. And that's what's called one hot encoding, and that's something that we need to do. Now I actually haven't written the function for that yet, and that's what we're gonna do right now. So define one hot encode. Now we could use, I am pretty sure there are ways that you can use to do this very quickly. But a really scalable and a good method that I found out was on Kaggle. There is this person who actually did exactly what I am doing right now, just with a little bit of different code, uh, and the one-hot encoding function that they use is what I am gonna go ahead and use for my case. And as you can see, even the ReLU derivative is taken from there. So as you can see, this is the one hot encoding function. I actually think that even this guy hasn't coded out what you are seeing over here, because I did see a Kaggle, I'm not sorry, not a Kaggle, but a Stack Overflow thing, which actually had this. So I'm pretty sure even this guy didn't code it out by himself, but it's okay. I mean, yeah, helpful for me. So, so I'm just gonna paste that, and that's it. So that's it for our one-hot encoding function, and now we can get started on our categorical cross entropy derivative. Alright, so define the categorical cross entropy. We are again gonna need the truth and the predictions. So truth and predictions, and we are still gonna have to do the same thing that we were doing, since in this case, if we look at the derivative, we are dividing it by the predictions, meaning that the prediction, if 0 in any case, will take my entire division and put me and give me an infinity, and therefore just breaking my derivative. And therefore we need to do the same thing that we were initially doing, which is clip the predictions between two values. So we're gonna have to do that. So yeah, so I'm just gonna go ahead and copy that over here, and we're gonna paste that right here. So we have clipped our predictions, and now we can just do a simple return. Actually, not return. I'm gonna do term one is equals to a simple uh, truth divided by the predictions, and then output is equals to negative np dot sum term one, and then you can just return output. I don't know if this will work or not, but we'll see. Alright, so now we can code out the backward pass for real. Okay, perfect. So as you can see here, we have the loss now. Now, if we construct the graph of our neural network, we know that the loss is going to be at the right hand side end of the chain, and the weights one and the inputs one in the inputs, like the original model inputs, are going to be on the leftmost side of the chain. So we have to work from right to left. So the first derivative that we have to calculate is just the derivative of the loss function with respect to the a2. So all we really need to do now is we just need to say a simple dloss. Now we will pass in the parameters for this function in a second, because I don't exactly know how many parameters I'm going to need. So that's just going to be equal to the categorical cross entropy, which is going to be called on the truth and the predictions. So truth and the predictions. So that means we need so therefore the params needed for this are the are a2 and actually wait a minute, yeah, a2 and y. So therefore train labels. Obviously we will take this in as y, but just saying. So then we need to do a d. Okay, so now let's look at this. So if you actually go ahead and work it out, I'll actually show you how. I'm actually gonna work it out on my whiteboard, and I'm gonna take a picture of it, and we're gonna try to develop an equation for the backward pass of a weight and a bias. And the reason why we are trying to do it is very easy, which is the fact that if we don't develop an equation, we're gonna have to rely on just intuition, and and just trying to do that entire thing without having any graph to help us out is not a very good idea, because there's a very good chance you might just make a very dumb mistake. And I mean, if you make a bad mistake in backpropagation, the problem is that it is a very difficult thing to debug, and so it is important that we don't make any dumb mistakes. Alright, so I've constructed the chain. So now what we need to do is we need to find out that given an A, if we need to find out the dB and the dW, so if we want to do a dA by dB and a dA by dW, what should we do? So first off, if we want to do a dA by dZ, I'm hoping you're familiar with my notation, and I'm expecting that the activation function is relu, then that's just going to be equal to the d relu of Z. Then if we are trying to do a dA by dB, well, that's just chain rule. That's just equal to dA by dZ times dZ by dB. And you can verify that by, if you look at the derivatives as a fraction, you'll see that dZ and dZ will get cut off, which will give you a dA and dB. And therefore, we know that a dA by dZ is just equal to the d relu of Z. So d relu of Z. And dZ by dB, on the other hand, if you look at that, is just equal to 1. So therefore, the dA by dB is just equal to d relu of Z. Therefore, if we have to write it down a bit better, dA by dB is equal to the sum, because you have to average off for all of the values of Z, because right now we are looking at a scalar, but when we are working with an actual neural network, we are considering a vector. So we just do a sum of I equals 1 to some n of d relu of Z of index I. And we can further write it down as something even better, which is we can write it down as the sum of I equals 1 to n of the d values of the ith index. So that means any activation function's output. So now let me take a picture and show you what it is that I have worked out. Alright, import from my part, take a photo. Alright, I wish there was a better way. I'm pretty sure there is, but I'm just too dumb to see it. Use the photo. Perfect. Alright, image2.jpg. Perfect. Alright, there we go. So as you can see, this is what I worked out. So we have a dA by dZ, which is just d relu of Z. And then you have a dA by dB, and this is where I said that you could cancel off the dZs if you interpret the entire thing as a fraction, giving you a dA by dB, meaning your thing is correct. This is our graph, if you just want some reference. And so if we get this, we know that dA by dZ is a d relu of Z, and then this entire thing goes off to 1, because Z depends on Q and B, which are added together. So if we use sum rule, this goes off to 1 and this goes off to 0, and since we are taking a product, anything times 1 is just that, and so we just get d relu of Z. We have to average it over, since currently we are considering that weights, inputs, bias, this intermediate Z and A are scalar values, while in reality they are matrices or vectors. And so we need to sum over all of them to kind of get the average, and therefore we just do that. And that's it for the bias. Yeah, that's just for the bias. Now we have to work out the weight calculation for it. And believe me, the weights are actually very simple to calculate. Also, they aren't too crazy complex. It's pretty simple. And the reason why I'm developing these equations right here is because if I can develop these equations right now, all I'll have to do is just chain them together in the backward pass function, and I won't have to actually develop them while we code it out, because then it will be horribly difficult. So therefore, I'm just going to write it down on one side that d bias is equal to the sum of I equals 1 to n, the d values of the ith index. So I'm just going to write it down, and I'm going to put like a box around it, a formula. Alright, and so now we can focus on the weights. We now know what the dA by dB is, and since we know that, if you have seen my last stream, you'll probably know this, that if you have a positive, if you have a plus sign, you can work this out by yourself. I will leave the proof as an exercise to the viewer. I mean, I'm pretty sure I went through the proof in my last video, but yeah, it's a very simple thing to prove. Please do it. But if you, and I'll tell you what the proof is. So if you have dA by dz, and then you have a positive sign over here, if you have a plus sign over here, then dz by db, I'm sorry, dA by db is equal to dA by dq in all cases, and you can work it out and see how that's true. I mean, since we don't have any actual values, actual constants, all of these are variables. If you solve it by yourself, I mean, it will be generalized to all values. So that's pretty neat. Alright, so now we have dA by dB. We can, so therefore, that is also equal to dA by dQ. I'm expecting that you know that what we just said is correct. And so now, what we can do is, we know dA by dQ. So now if we want to do a dA by a dW, because that's all we need, we don't need dA by di, we can just say that dA by dW is equal to dA by dQ times dQ by dW, which tells you that since we know that dA by dQ is equal to the dRelu of Z1, and then if it's dq by dw, since the I and w are being multiplied, w is raised to the power of 1, therefore w goes off to 1, and then I remains as a constant multiple, which is multiplied by dRelu. We get that dq by dw is equal to a dRelu, or the d values if you don't understand this d values notation, I actually got it out from a book, the one that I looked at in my previous video, neural networks from scratch. If you want to check it out, do check it out. But I did differentiate these functions by myself. I didn't copy that from anywhere. So yeah, and then we have your I. Now in this case also, we're gonna have to sum over them, because I'm pretty sure we're gonna have to sum over them, because we are considering them as scalars right now. So I'm gonna check if we do need to do that or not. For till then, I'm just gonna give you what the equation we have developed right now looks like. It does look a little involved, but I hope you understand. There we go. We have our third image. So as you can see, we have our dA by dB, and then I just wrote out dA by dQ times dQ by dW, which gives you simple, and actually made a little error. It's not dQ by dW in the last line, it is equal to dA by dW. So yeah, I just made that teensy little mistake. No issue in my actual output, just saying. Alright, so we have the derivatives in place. All we have to do is just put them together in the backward pass. I don't know how long I've been going for at this point, but I mean, this stream is kind of mathematical and complex, so it's definitely something that is a little challenging even at my end. Alright, so now we have d loss. So what we need now is we need dB2, and that is actually just, and before we even get dB2, we need d sigmoid, right? Because, and d sigmoid is technically being applied to is technical. So okay, let me see. So if we have a, and then we have our loss function, so that's going to be sparse categorical percentropy. 1 second, and that gives you your logits. We have the d loss. So now when we do that, we need a, but at the same time, I don't understand, do we need a or something else? So if we are trying to do something like this, so currently what our chain looks like is we have added another term, which is our loss term, categorical percentropy. And if we are trying to do a dl by a dz, that's equal to the dl by dA times the dA by dz by chain rule, right? So if we do a dl by dz, that's equal to a dl by dA times a dA by dz. And dl by dA, we already know that it's just d categorical entropy times the dA by dz, which is equal to the d value of z. So we have the d loss right here. Okay, so in this case the d loss is going to be our d value. I mean, I know this sounds kind of crazy, but that's what backpropagation is. So I'm just gonna look at this article right here. So for the dw, what is it that they did? So they have your dz2, and then they have the a1 transposed for the dw2, and for the dz2, that was the a2. Okay, so I don't understand why they did this for the dz2. I don't understand that, but I'm not gonna do that. Alright, so I'm gonna just stick to what I think is correct. I hope I hope that it's correct, but who knows. So dz2 is equals to d loss times d value of z2. I'm pretty sure that's not correct, and also I'm not sure if I need a I'm pretty sure I need a multiplication. And another thing that I'm not sure about is that this, so do I need a np dot sum over here or not? Not sure. So then if I do a dv2, that's a np sum of the d values, and the d values in this case are going to be equal to the d value of z. So in this case that's equal to dz2 and then a dw2 is equal to d. I'll have to see that. Just one thing I'll have to see is for the dw2, okay, we need a dot. So for the dw2, that's equal to the d values times the input. So we're gonna need the a1 and the d values. So we do a simple np dot dz2 and input. So that's equal to a1. I'm pretty sure what I'm doing is completely wrong, but I mean, I don't exactly have any better option. So for dz1, actually no, dz1 or da1. I mean, even if I ignore that, and I also remembered that I made another mistake. This should be d sigmoid. So over here for da1, what I think I'm having a bit of an issue in understanding is that we have I mean, if we just use the equations that we developed for the d bias and the d weights, I mean, we'll still need that. So in this case, what can I do? So for da1, we have the, okay, I'm seriously blanking at this point. I'm not understanding exactly what else I can do. But one thing that I think I understand is the fact that when you have a multiplication sign, one term of the derivative will remain the same and then the other term will just change up. So technically this should be a np dot of dz2 and the weights too, I'm guessing. Let me look at that. Weights to dot dz2 times the value to derive that. I'm pretty sure. Yeah, so that's correct. That's exactly what these guys did. And then this is the A1. When what we need is, so if we go on to dz1, that's equal to the d value of dA1. And then for dB1, it's an NP sum of dZ1. And for dW1, that's a NP dot dot between dZ1 and dB1. So if I do a return of dW1, dB1, dW2, dB2. I'm pretty sure I've made like a million bugs in just this piece of code, but we'll see. So we have Y and over here for the truth, then this should go off to Y and predictions should go off to A2 then I need Z2 W2 what else pretty sure that's it. So then if I do a simple define update params on the equation for gradient descent, we'll need W1, B1, W2, B2, dW1, dB1, dW2, dB2, and then we can just say a simple W1 is equals to W1 minus some alpha, which is actually non-alpha, eta, which is equal to your learning rate minus eta dW1 W2 is equal. So then we can just paste this and get the update params for W2 and B2 also. W1, B1, W2, B2. Cool. I guess that's it for the update params. So now we can do a step. Actually, not step. We can do a simple gradient descent. Actually, I mean gradient descent is actually not a correct function name, I would say, because technically this is gradient descent, but yeah. So iterations, and we're also going to need a bunch of parameters for this, but we'll see. Alright, so for gradient descent, we obviously first need to initialize the parameters, initialize the network parameters. So I'm gonna copy this. Initialize network params. What was the full name? Yeah, params. So we have that. We have the weights and the biases. So then we can do a for I and range for the iterations, and technically it should be something like iterations plus one. Alright, so yeah. And actually, you know what? I don't think I need the plus one because this goes up to 0 to iterations minus one. So yeah, that's okay. Alright, so now that we have this in place, what we need to do is we first need to perform the forward pass. So we can do a simple forward, and for that, and also here for the, so we can go ahead and take the input of x over here, so we can then just say a simple forward which is equal to z1 a1 z2 a2 loss forward on x w1 b1 b2 and now we need to write out the backward pass, but is it correct? I'm guessing. Let me just check. Yeah, it is correct. Backward and then update. Yeah. So let's write out the backward pass. So we have the dw1, the db1, the dw2, and the db2, which is the backward on the y a2 z2 w2. Define y in the function parameters, and now we need to update the parameters again. Alright, this is like hard work. Super redundant stuff. Alright, so for that, I mean, we basically need the same things. And yeah, that's pretty good. That's it. Yep. So then finally I can do a simple return w1 d1 w2 b2. Alright, so now I can go down and call gradient descent, and also red training, and we're gonna run it over the train images. Train tables. Oops. Or let's say 100 iterations right now. Alright, so if I open up a new terminal window and just do a Python 3 main.py. Oops. I don't know. Okay, yeah, it is main.py. So we can run the main.py file now, and maybe it should work. If everything is working, we should see done training show up, and internally also everything should work. I hope none of my shapes are messed up. I should probably print that out. Okay, this is taking some time. The main problem with this entire thing is that it's not that I don't understand how the math works. It's the fact that the it's really hard to actually put the math into code. when you aren't using like actual good programming practices. What I mean is like I tried doing this with classes and objects, and it was just so much more easier to do. Alright, so I need to do that first. And I also didn't remember one thing, which is the fact that y right now isn't not encoded, so I need to do a y is equals to 1 encode y, and I'll have to 1 or encode y with the also, so I'll need to copy this, really paste that right here. And for the forward pass, where's the forward pass? We have a y here, so we will need the y input over here, and d loss is equals to not d loss, I'm sorry, y is equals to 1. Alright, so right now we just had an issue in our forward pass, which is not a good thing because we still haven't reached our backward pass yet. I mean, also keep in mind that the calculations that we are doing here are in no way ideal computationally. So we might take a lot of time to run this model, even though it's on such a basic data set. And that's one of the reasons as to why we don't write models like in native Python. It's just too slow for actual tasks. Also, one thing is because Python itself is a very slow language, and I mean I know for a fact that numpy is actually built on top of like C or C++. I don't exactly know which one, and so yeah. Okay, wait a minute. Uh, okay, so I'm ignoring one. Okay, I mean yeah, I understand what's the issue here. Alright, so we still haven't reached the backward pass, which sucks, but okay, so I need to do a y here. That's it. Alright, please work. I'm pretty sure that the only thing in the backward pass that just give will throw me an error overall without like a, if we don't keep a logical error in mind, is that some of the shapes won't work, and I might have to put like a transpose somewhere. But that's not too bad. So yeah, I hope, because I think pretty sure the error I'm gonna get is gonna be like some sort of a logical error when s- some of the arrangement of the DZs and the DWs is kind of wrong. Alright, and I mean, really, the best way to solve a problem like this is to just use classes and objects to just structure your code and make it so that you can differentiate all of that. Alright, okay. Uh, Amax. What do you mean? Alright. What do you mean? I mean, I do have a Amax. It's right here. Let me see. And now if we just do a x is equals to 0, 1, 2, 3, 4, and then we can just do a simple x is equals to np dot array x, and I'll need to do one more thing, which is that, so that I'm gonna click it. What do you mean? I'm gonna have to Google this. Oh, I guess I understand what my error is. I'm guessing I understand, but I don't know. I mean, I am specifying aim, and I mean, that's right. Alright. I just hope that this works at this point. I seriously don't know what else I can do. Okay, that worked. Cool, so I just really need to get rid of these things. I don't know why I put them in the first place. Maybe just to make this look a bit more neat. But whatever. If it doesn't work, then it doesn't work. Alright, let's run this now. Now, that was a lot of errors before we even got to the backprop part. It's kind of crazy, but let's see. Alright, this is taking a second. Please just don't throw me any errors. I seriously, I can't look at any errors right now. Alright, this is taking a second. And that was exactly the error I knew I would get. Yep. I need to transpose my prediction in categorical procedure. Alright, that's okay. Okay, so I need to take my prediction and I need to transpose that. Perfect. Because it's 60,000 by 10, so if we go 60,000 by 10, 60,000 by 10, and then we add those two together, we should just get 60,000 by 10. Which means it should work. See, so in this case, as you can see, the error is really kind of easy to debug because I mean they're telling us the exact line, and that I mean if you know the shapes that can't broadcast together and you know the operation that's happening, then you can kind of figure out what's the problem. Because right now the issue is not the fact that I'm pretty sure that the issue is that we aren't able to add the truth times prediction of the I minus 1th index with the truth plus prediction of the ith index. Local prediction reference before assignment. The categorical percentage P, the categorical percentage prediction. That's the. As you can see, small errors. That's what we need to avoid. And how long have I been streaming for now? 48 minutes, pretty neat. Today's stream has been quite smooth. I mean, I was expecting I would get like a million technical difficulties, but cool thing, I mean, I don't have any of those. It's taking a second, obviously, to run this entire thing. I mean, the backprop steps are kind of crazy, and they are written very badly. I mean, if you really want to develop like a neural network library, I would highly recommend that you spend a lot of time with optimization of your calculations, because right now the techniques that I am using, I mean, they work, but I'm not even sure if it's the fastest for the computer to calculate stuff like this. And I made some stupid issue again. Local variable prediction reference before assignment. I'm pretty sure the error right now is actually the fact that didn't spell prediction correctly somewhere. Oh, there we go. So this is the bad thing. I mean, I have to wait so much of time. All right. I mean, the chart is quite empty, so that's something. All right. We had a viewer. It's pretty neat. All right. It's taking a second. I mean, I know that a lot of it, the time is for actually loading in the data set, the administrative digit data set. And I mean, also the another reason why it's taking as much of time it is taking is because I am actually doing this on stream, so a lot of my system resources are being used up to actually keep the stream on rather than actually run the code that I'm writing right now. So that's one of the issues, I would say. Because right now I still haven't actually. Alright, cool. So we ran into our error again. Luckily, I know what the error is. I just need to transpose the truth thing. I don't know what else to call it. So we can say a simple truth dot transpose. I mean, I don't even know if I will be able to finish this in the stream. I might just come up with the third stream, debugging. Seriously, I mean, we literally came across like 5 to 6 errors just in the loss function code, and we still haven't even gone to the backpropagation functions yet. I mean, we are still just at the categorical entropy right now, and the main issue is gonna be just getting the shapes right first, and then actually, making sure that the equations that we have are correct. And to be honest, the problem right now is the fact that actually making sure that we have the derivatives correct is actually pretty difficult to figure out. Okay, so a1 is not defined. I just need to take that in as a parameter. Alright, so I'll just need that as a parameter. So I'll just do a simple a1 over here. And so that means that over here, when we are actually doing this, I'll need to specify a1. Where should I specify that? Right here. Alright, cool. But when did we get to A1? Oh, cool. So we did reach DW2. So we managed to get to these calculations correctly and DLOS correctly. So now we are at DW2, which is cool. So that means that DB2 was successfully calculated. And I know for a fact that DB2, the equation is correct. I just hope that the inputs are correct. Alright, I mean, it is taking a second. I mean, I wish I could just do this off camera because it is taking so much of time to do this. And I mean, it still hasn't loaded in the data set, I guess. Actually, no, I think it has loaded in the data set. It's going through the calculations. I think the main issue that I am facing right now is the fact that I'm running the thing for 300 iterations, meaning it is going to take a lot of time. So let me check to see exactly how many iterations this thing was run for. Oh, it shouldn't be 300 iterations. It should be more like 10 iterations. Ah, that was my error right there. Oh wait, I just ran it for 100 iterations, but yeah, I'm just gonna run it for 10. Oh, come on. I have to quit this. Terminate the process. Open up a new one. But at least I know that my shapes are working. Because I mean, if we didn't get any issue with the backward pass for just one epoch, one iteration, then we shouldn't get that for several iterations. And if you are wondering why I'm using the term iterations instead of epochs, that's the reason, because uh, there's a difference between iterations and epochs. Iterations is the steps that you take per epoch. So when you'll be training a model, you'll see that you'll be like the first step of 100 steps, the second step of 100 steps, and after you finish those 100 steps, you get to the second epoch, and so on. And so those steps are your iterations, and then those epochs are your epochs. So if you would have one epochs, you would probably need to have a for loop over here also. But I mean, we are not doing that in this case. I mean, you could do it, but I'm not going to do that. At least I'm pretty sure that's correct. All right. So let's just hope that this works. I don't think we're gonna deal with predictions. Uh, Dealing with predictions is pretty easy to do. If you just want to figure it out, I'll leave that as an exercise. I just hope that it works. This works, and I might probably off camera verify if the calculations that we have match with the code that we have. But I just hope that this specific thing works. If it works, we can end the stream right now, and yeah, it should be good. I mean, oh wait a minute, what's happening? You know what? That's okay. I mean, it's not like, I mean, we are still just running the code. I do think that it's gonna take us a lot of time to actually go through even these 10 iterations. I just should have just had one iteration, I guess. I still have time to do that, but we'll see. Because the aim for this video series, the stream really, was not to have the best model in terms of accuracy. It was just to show that this is possible and doable. And so that's really all I was trying to do, not actually have a really good accurate model, because I mean I don't have GPUs and stuff, so that's one thing. And the second thing is the fact that the calculations that I'm doing are pretty slow, and computationally bad, inefficient. It's also taking me a very long time to load in even just the data. I mean, it's still currently just loading in the data. Now it finally pretty sure managed to load in the data. Alright, so we'll wait for some time, and if it just doesn't work, I mean, what I mean is if it just still takes us a long amount of time, I'll end the stream right now and do the entire running part off camera, and I'll probably make a video on this in like tomorrow or maybe something like that, and I'll go through exactly what it was that we managed to do and stuff like that. Alright, okay. So now the dimensions are aligned. Okay, I mean, all I have to do is just transpose something with this. But then I have another issue, which is the fact that if I transpose this, wait, okay, so we are at DW2. Okay, I have a feeling that I need to transpose DW2. Also, another thing I'm gonna do is just run it for one location. So for DW2, I'll need to transpose DZ2. So if I transpose that, let me see one thing. This guy actually wrote down exactly what the shapes should be for the derivatives. So for DW2, it should be 10 by 10. Let me see. Wait a minute. If for DW2, we have A1, which should be 60,000 by 150. In this guy's DW2, they are saying that the shape should be 10 by 10. And for DW2 over here, okay, so we have DZ2, which is 10 by A2. I mean, I understand why it should be 10 by 10, but yeah. So I'm guessing it has to be an A2 over here and not an A1. That's my guess. So we do an A2 here, and then I don't know what A2 is in terms of shape. So I'm gonna have to check that. So A2 is gonna be equal to, right, so Z2 is A2 10 by M. In our case, it's gonna be M by 10. So if that's M by 10, we have to do a transpose here and a transpose here. Alright, let's see. Hopefully it works out. Alright. If I mean, I swear, if it doesn't work in this, I will just make a video on it. At least I hope that I get some progress. I mean, we move on from DW2 and we actually move on with valid shapes. I mean, it's just taking so long to even load in the data. I mean, it's so much of that. You know what? I think I've gotten. I mean, it's literally taking me a minute to load in the data, then like another 2 minutes to just run the model. So debugging this on camera is kind of a pain. And so yeah, I mean, because other models, I usually use TensorFlow, so it's a little quicker because at least the calculations are a little more snappy. I do think that I made a mistake. I shouldn't have done this in like when on my local machine. I should have just used like Google Colab. But I mean, at this point, I seriously can't be bothered to copy paste all of this in like different cells and stuff because I'm basically done with all of this, so it doesn't really make any sense to do that. But I mean, yeah, I do think that that was a stupid mistake. Oh, what's happening? My terminal is literally lagging at this point. Alright, so you know what? I'll get to this in the